Okay, I think we can start. This is the last lecture today. We probably won't need the full 80 minutes, maybe just 60. We'll see how it goes. We're going to finish the proof of Priceman's theorem. Then I'll prove a related result. And then if we have time, we'll do a generalization of Priceman's theorem called Bayer's theorem, which is basically just putting in some more group theory into the proof of Priceman's theorem. Before we start, so you've all handed in assignment 4. I'm marking it. You'll get it back, I hope, by Friday. I think assignment 5 is due a week from today, right? On Monday of next week. It's only 3 problems, so feel free to finish it quicker. And I'll mark that within 48 hours of the due date. Any questions about any of that before we start? Okay. So this was Priceman's theorem. It tells you something about the fundamental group of a compact Riemannian manifold that has negative sectional curvature. We started doing the proof of this. We did about half of it. I'll review the steps that we've established so far. And there was also something else from last lecture called the translation proposition. Basically, that thing, without writing it down, because I'm going to use it, I think I'm going to use it a couple of times today. That proposition said that if you had if you have a compact Riemannian manifold and you take a deck transformation, that's not the identity. So an isometry, a covering transformation of the universal cover, then that's a translation. And remember, what a translation meant was that it was a translation along some geodesic. That meant there was some geodesic whose image set was preserved by that isometry. Okay, so Priceman's theorem says if we have a compact Riemannian manifold with negative sectional curvature, and I take a subgroup which is not trivial, which is not the trivial subgroup, which is also abelian, then this subgroup has to be infinite cyclic. And you can turn this around if you have this result is just topological. So if you have a compact manifold whose fundamental group doesn't have this property, that every abelian non-trivial subgroup is infinite cyclic, then that manifold cannot admit a Riemannian metric with negative sectional curvature. Okay, so this is what we want to prove. We proved 2 claims last time, and when we do the sort of variations of this idea after we finish the proof of this, I'm going to be referring to these claims again. We're going to need them. So the first claim, which we did, was we look at the projection onto the universal cover. We say if you take any translation, if you have a translation of m tilde along some geodesic gamma tilde, then that's the only geodesic that's left invariant by this isometry F. And this uses, in a strong way, that K is less than 0. Okay, because this is not true, for example, in flat space. Their translations will have infinitely many distinct geodesics that are invariant. So we proved that, and that was with the triangles, the geodesic triangles and the geodesic quadrilateral. And I made that a little more complicated than it needs to be, but I think I clarified it on Piazza after class. And then the second claim, which was an immediate corollary of the first one, was if we have some other isometry without fixed points, which commutes with a translation, which is not the identity, a translation along some geodesic, which is not the identity, then this other isometry is also a translation along the same gamma tilde. Okay, so that's where we ended last time. Now we're ready for claim number 3. Claim number 3 says if all the elements of a non-trivial subgroup, non-trivial just means it's not the identity of, not the trivial group, non-trivial subgroup H of pi 1, considered as elements, did I do this too? No, I didn't do this too. As elements of the group of deck transformations, leave invariant a fixed geodesic gamma tilde, then H is infinite cyclic. And you can see almost immediately how the theorem will follow from these 3 claims, but I'll spell it out carefully when we get to it. So let's just make sure we understand what this says. Remember, there's an isomorphism between the fundamental group and this group of deck transformations. It's not canonical, depends on some choices, but it's a group isomorphism. So if you have some subgroup which is not trivial of H, and every element of H, when you consider it as a deck transformation, it leaves invariant the same geodesic gamma tilde, then this subgroup H has to be infinite cyclic. So I'm going to slightly modify the argument that Do Carmo gives because it's full of gaps, I think. I found this version, I believe, in Peterson's book. So here's the proof of claim 3. Much more transparent this way. So let H be an element of big H and not equal to the identity, which exists because H is a non-trivial subgroup. So we claim that H composed gamma tilde of T is gamma tilde of T plus A theta. Let's call it theta. Theta H for some real number theta H. So in other words, H, remember, it's in pi 1, and I'm thinking of it now as an element of the group of deck transformations. So this is an isometry of the universal cover with no fixed points, right? Because the deck transformations is exactly the group of covering transformations. If it's not the identity, then it has no fixed points, and they're all isometries of the universal cover. So we know, since gamma tilde is a geodesic and H is an isometry, we know that this is a geodesic, and the assumption is that it leaves gamma tilde invariant. So it has to take it has to take gamma tilde of S to gamma tilde of something else. Okay, and we're claiming that it translates everything. It really is just a translation of the time parameter. So H composed gamma tilde is a geodesic of M tilde. That's because gamma tilde is a geodesic and H is an isometry, and H leaves gamma tilde, the image of gamma tilde, invariant. So H of gamma tilde of T is gamma tilde of something, right? And that something will depend on T. And what we're saying is that for any T, they're just translating the time by the same amount, which only depends on H. So, so let's see why. So to see this, first of all, notice that H gamma tilde prime, if I look at the velocity, this is H star at gamma of T applied to gamma prime of T, and that's equal to gamma prime of T because H is an isometry. So if gamma is normalized, gamma tilde is normal, gamma tilde, sorry. If gamma tilde is normalized, so is H composed gamma tilde. They take an isometry will take normalized geodesics to normalized geodesics, and we know that the image of H composed gamma tilde is equal to the image of gamma tilde. So H composed gamma tilde is a reparametrization of gamma tilde, preserving the unit speed, property. Okay. So if it's going to still be unit speed, and it's a reparametrization of gamma tilde, all we can do is translate the time parameter, and we can possibly also change the direction. Okay, so then, so H composed gamma tilde of T is plus or minus T plus some theta, which depends on H. Okay, so this is all the reparametrizations of a geodesic are affine linear reparametrizations. It's a constant times T plus a constant, and that constant changes the speed unless its absolute value is 1. So the constant has to be plus or minus 1. So let's rule out, all we have to do is rule out the case of -1. And that's where we're going to use the fact that H is not that H has no fixed points. So if H composed gamma tilde of T was minus T plus theta H, let's see what happens here. Evaluate at T is equal to theta H over 2. What do we get? We get that H composed gamma tilde of theta H over 2 is equal to, oops, I forgot my gamma tilde, is equal to gamma tilde of theta H over 2. And this says that H composed gamma tilde, H leaves gamma tilde of theta H over 2 fixed, but H is not the identity, so it has no fixed points. That's right. And therefore, that's a contradiction. And so the only thing that, let's see, what goes wrong here? Nothing goes wrong, right? Oh yeah, my assumption was H was not the identity. Okay. And of course, if H is the identity, this claim, subclaim in claim number 3 is trivial because you just take theta H to be 0. Okay, so H composed gamma tilde of T equals gamma tilde of T plus theta H. Okay, now consider the map from this subgroup H into the reals. I'll call it theta, which sends little h to this element theta sub H. Okay, so it's clear that theta is a group homomorphism. So why is that? Theta of H inverse, if H translates gamma tilde by adding theta H to it, and H inverse is the inverse of H, then H inverse will translate gamma tilde by minus theta H. So theta of H inverse is minus theta H, and theta of K times H is theta K plus theta H. Okay, so here this is the additive group structure on R, right? It's an abelian group under addition, and this is a group homomorphism from here to here. Also, we claim it's injective. Suppose H is in the kernel of theta. This means that theta sub H is 0. So H composed gamma tilde equals gamma tilde. Right? If it doesn't translate at all, then it has fixed points. This implies H is the identity. So the kernel, so H is an injective group homomorphism. Okay. Therefore, we can think, sorry, theta. Hence, its image is a subgroup of R isomorphic to H. Okay, because it's an injective group homomorphism, it's an isomorphism onto its image. And now we use a fact from group theory that if we have a subgroup of R, the additive group R, it's either dense in R or it's infinite cyclic. So now it's a fact from group theory. Any subgroup, non-trivial subgroup of R under addition is either dense in R or infinite cyclic. But it can't be dense in this case. So since the isometries in H, so the elements of H are deck transformations of the universal cover, they operate in a discontinuous way. What do I mean by that? I'll tell you in a second. Discontinuous way. So H is not dense. I mean theta H here is not dense in R. So what do I mean by discontinuous? For all points in M tilde, there exists a neighborhood W containing P tilde such that H of W intersect W is empty for all H not equal to the identity. Right? This is because it's a covering transformation. Everything except the identity is permuting the sheets around. Right? So if you take a neighborhood small enough that it's contained in the domain of a single sheet, then all the non-identity elements of the group of deck transformations will permute those around. So therefore, it can't be dense. Therefore, it must be infinite cyclic. So theta H is infinite cyclic, and that means that H is infinite cyclic because it's isomorphic. And that's the end of claim 3. Okay, so now we can finish the proof. Now we finish the proof of Priceman. And as I said, I'm going to refer to these claims again afterwards. So suppose H is an abelian subgroup, non-trivial subgroup. We have to get a contradiction. Okay. So every little h in big H, which is not the identity, is a translation along some gamma tilde geodesic. This is by the translation proposition from last time. The translation proposition said that if we had a deck transformation which was not the identity, then it was translation along some geodesic. By claim number 1, every H, which is not the identity in H, leaves invariant a unique geodesic. Claim number 1 said exactly this, right? That if you took a non-identity deck transformation, there's only one geodesic that leaves invariant. By claim number 2, since H is abelian, this is where we use it. All the elements H in H not equal to 1, leave invariant the same geodesic. Right? Claim 2 said if you had a translation along gamma tilde and you had some other isometry without fixed points that commuted with that first isometry, then it's also a translation along the same geodesic. Each one of these is a translation along some geodesic which is unique, right? But they all commute with each other because the group is abelian. And therefore that geodesic is the same for every single one of them. But then by claim 3, that's exactly the setup we have in claim 3. We're saying if we have a subgroup which leaves invariant, all leaves invariant the same geodesic, a non-trivial subgroup, then it has to be infinite cyclic. H is infinite cyclic. Okay, so that's the proof of Priceman. Let me give two examples, and then we're going to slightly modify this. So example, Tn, which is the n torus, n copies, for n at least 2, does not admit any metric of negative curvature, because pi 1 of the torus is n copies of Z. Okay, so if n is at least 1, then this definitely has non-trivial subgroups. In other words, the whole, you can take the whole thing, which is not infinite cyclic. Okay, and of course, when n is 1, S1 is always flat. Any metric. So any metric on the torus will have to have points on it where the curvature is 0, sectional curvature is 0 or positive. Can't be negative everywhere. Okay, that's one example. There are others you can talk about, but let's just move on. So we'll generalize Priceman to Bayer's theorem soon, meaning in like half an hour. But first, we get a related result. Which needs a lemma first. Okay, so let's call this the no. This is a theorem. Let's call this the non-abelian theorem. This is my non-standard notation. So Mg compact K negative, then pi 1 is not abelian. So you see, once we have this theorem, it's even faster to show that the torus can't have a metric of negative curvature because its fundamental group is abelian. I don't have to worry about non-trivial subgroups having to be infinite cyclic. Okay, so this is, but it's not quite the same statement, right? Because the first statement says any non-trivial abelian subgroup has to be infinite cyclic, and this tells you forget about infinite cyclic. The fundamental group itself cannot be abelian. Okay, so to prove this, we need a lemma first. So proof. The first lemma. This is more general. If Mg is a complete Riemannian manifold, with non-positive curvature, and there exists a geodesic gamma tilde in the universal cover, M tilde, G tilde, invariant under the group of deck transformations, then M is not compact. The only way this can happen, if you have a complete Riemannian manifold of non-positive curvature, if there is a geodesic invariant under the deck transformations, it has to be a non-compact manifold. This is an interesting argument, very general. So proof of lemma. So let gamma tilde, we'll do this by, we'll show that M is not bounded. Let gamma tilde be the geodesic in M tilde invariant under A of M tilde. Fix a point P on the image and a real number, positive real number T. And consider, let me draw a picture. I have my colors this time. Leave them on there and hope I don't trip on them. So here's the picture. There's P tilde. This is gamma tilde. Another one, orange. Consider the normalized geodesic beta tilde from 0t to M tilde with beta tilde 0 is P tilde and beta 0 prime, beta tilde prime 0 is orthogonal to gamma tilde prime 0. So in the picture, beta tilde comes out from P tilde orthogonal to gamma tilde prime. Not the normalized geodesic, but unnormalized geodesic, right? Because I get one of these for every choice of orthogonal direction. And I'm going up until beta tilde of T. Okay, this T is the T that I fixed. I know these are defined for all time because M was complete, so its universal cover is complete. And now, let beta be pi of beta tilde and gamma be pi of gamma tilde. These are both geodesics in M because pi is a local isometry, and let P be pi of P tilde. So we'll draw this picture again. That picture is in M tilde. Now I'm drawing the picture in M. So this is beta of T. Let alpha T be a minimizing geodesic in M joining P to beta T. I want to go the other way, it doesn't matter. Joining beta T to P. So that's going to be okay, these are 2 points in M. M is complete. So every 2 points can be joined by a minimizing geodesic, not necessarily unique, but I know I have this minimizing geodesic. It might be beta, but there's no reason for it to be beta or beta inverse. And let's let alpha T tilde be the lift of alpha T to M tilde starting at beta tilde of T. I'll draw it. I'll draw it in a minute, but I want to observe something before I draw it. Actually, maybe I'll start to draw it. So this is in green, alpha tilde of T. This point is beta tilde of T. So since gamma tilde is invariant under the group of deck transformations, the endpoint of alpha tilde t, the final point, yeah, the final point of alpha tilde t belongs to the image of gamma tilde, because pi of alpha tilde t of 1 is equal to alpha t of 1, and that's p, right? So alpha tilde t is a lift of alpha t. Okay, that means pi compose alpha tilde t is alpha t. And this one ends at p. And what does the group of deck transformations do? It permutes it permutes the sheets above p, right? The inverse image of p gets permuted around. And because the group of deck transformations preserves gamma tilde, wherever this point goes, it has to be somewhere, it has to end on gamma tilde. Okay, so I mean, so let me finish writing it. These are permuted. Let me say it this way. So alpha tilde t of 1 is in pi inverse of p, and these are permuted by the group of deck transformations, but gamma tilde is invariant under A of m tilde. So this calculation says that wherever this point is, it's in pi inverse of p. Okay, so it's going to be equal to the some deck transformation applied to p tilde. But p tilde is on the image of gamma tilde, and the deck transformations preserve the image of gamma tilde. So it looks like this. And now we're almost done with this lemma. This is the neat part of it here. So since the manifold is non-positively curved, so is its universal cover. The geodesic triangle problem on assignment 4, question 5, says that the length of alpha tilde t is at least the length of beta tilde, which is t, right? This is a geodesic triangle. This guy's a geodesic, this guy's a geodesic, this guy's a geodesic, and the curvature is non-positive. So that means that this length, from that generalization of the law of cosines you had, we know that this length is at least the length of this. But this is a normalized geodesic from time 0 to time t, so this length is t. So the length of alpha tilde is at least t, but the length of alpha tilde t is equal to the length of alpha t. This is because pi is a local isometry. Right? If you write down this as the integral of the speed and use the fact that pi of alpha tilde t is alpha t, you get these lengths are the same. And this is less than or equal to the length of beta because alpha t is minimizing from p to beta t. So this curve here, this yellow curve is has the minimum length from between any curves between these 2 points, and beta is another curve between those 2 points. And this is equal to the length of beta tilde, again, because pi is a local isometry, and that is equal to t. Okay, so what have we shown? We've shown that L of alpha tilde t is at least t. That uses the negative curvature here. And here, I just use the construction of how I chose alpha and alpha tilde and beta. We get the other inequality. So L of alpha tilde t, L of alpha, L of alpha t, sorry, these are equal, right? So this is less than or equal to t, and it's bigger than or equal to t. So L of alpha t equals t, but t was arbitrary. So M is not bounded. Because remember, alpha t is a minimizing geodesic. Right? Just because I can find curves of arbitrary large length in a manifold doesn't mean it's bound, it's unbounded. But if they're minimizing geodesics, it does, right? Because the length of this curve is the distance from these two, between these 2 points. And I found a point for t, t could be anything I want. I found a point which is as far from p as I want in distance. So M is not bounded, and that means M is not compact. Okay, so that's the end of the lemma. We're doing really well on time. So let me remind you what the theorem we want to prove is. Recall that we're proving what I call the non-abelian theorem. Mg compact, k negative. This implies pi1 of M not abelian. And we showed the lemma Mg complete, k non-positive. What was the if there exists gamma tilde geodesic in M tilde invariant under A of M tilde, that implies M is not compact. Okay, so we want to use this lemma then to finish the proof of the non-abelian theorem. Okay. So suppose pi1 is abelian. We need to get a contradiction. Mg compact and alpha a deck transformation, that implies that alpha is a translation along some geodesic gamma tilde in M tilde. This was the translation proposition from last time, which we already used to prove Priceman's theorem. And that needed the compactness. Okay. So but then, since pi1 of M is assumed to be abelian, by claim number 2 in the proof of Priceman's theorem, gamma tilde is invariant under all the elements of AM tilde, right? Because Priceman's theorem, claim 2 for Priceman's theorem says that if you have some translation along gamma tilde and you have another element of the group of deck transformations which commutes with it, then it'll also be invariant, and it'll also leave the same gamma tilde invariant. But we're assuming that pi1 is abelian, so all the elements of the group of deck transformations commute with each other. Okay, but then the previous lemma says M is not compact, and that's our contradiction, right? This previous lemma, we're compact, so we're definitely complete, and we're negatively curved, so we're definitely not positively curved. If you had some such geodesic invariant under everything, it can't be compact. Okay, so now we've shown that if you have a compact Riemannian manifold with negative curvature, its fundamental group can't be abelian. In fact, we can do better. We can generalize both Priceman and this non-abelian theorem. And it's gotten better even since this book was written. There was much more progress made in the 70s and 80s on the questions of fundamental groups of negatively curved compact manifolds, or not even non-positively curved. They've pushed it a bit, but we're not going to get into that. So we have time. So here's the last theorem I want to prove in the course. This is due to Byers. Again, the same assumptions. Let MG be compact and negatively curved. Priceman said that any non-trivial abelian subgroup had to be infinite cyclic. This theorem said that pi1 itself had to be abelian. And this theorem says, suppose H in pi1 of G, pi1 of M, is a solvable subgroup. I'll tell you what that means in a second. Solvable subgroup. If H is not equal to 1, then H is infinite cyclic. Okay. So this is a generalization of Priceman. Oh, moreover, pi1 of M does not have a cyclic subgroup of finite index. Okay. So let me make a. I'll explain what solvable is in a minute. Let me make a remark. We already know here, this cyclic subgroup must be proper, right? Otherwise, there's no content to this statement, because if I take the whole pi1 of M, that's a subgroup of index 1, right? The order of the quotient. But that would mean, pi1 is cyclic, and that would mean it's abelian, because if not, H equals pi1 is abelian, and that contradicts the theorem we just proved, right? We have the assumptions. We know that pi1 is not abelian. So the only time you can even consider having a cyclic subgroup is if it's proper. And this theorem says that there are no cyclic subgroups of finite index. So what is a solvable group? So remark, a subgroup H of a group G is solvable means if and only if there exists a finite sequence of subgroups. So the first one is H, and then H1, H2, these are proper inclusions, HK minus 1, HK, this is the identity, the trivial group. such that hi plus 1 is normal in hi, and therefore we can take the quotient, and hi over hi plus 1 is abelian. Okay, so this is a very strange condition, unless you're a group theorist, to impose on a group. But an example, if H is abelian, we can take H to be H naught, and then H1, we can just stop this going from H to 0. Then certainly the trivial group is normal in here, and the quotient is abelian because the quotient is H. This is solvable. Okay, so every abelian group is solvable, but not every solvable group is abelian. So abelian subgroups are solvable, but in general, not conversely. So this is telling you much more about the fundamental group, the structure of the fundamental group. So let's prove this now. I have enough time easily. We're definitely going to finish early. So here's the proof of Byers. Really, we're going to just use the two theorems we proved today, Priceman and the non-abelian theorem. I think we are. Yes, we're going to use the two theorems we proved already today to prove this one, which is why we couldn't just go right to this. So suppose H is solvable. What is this statement, right? We have to, if we have a solvable subgroup, we have to show that it's infinite cyclic. So why is this a generalization of Priceman, right? Because I just showed that any abelian group is solvable, and Priceman said if you have an abelian subgroup, which is not the identity, then it has to be infinite cyclic. But it's not just for abelian subgroups, it's for solvable subgroups, which is more general. Okay, so suppose H is solvable. So star holds. Let's make this thing star so I don't have to write it again. This is the definition of solvable. In particular, hk minus 1 is equal to hk minus 1 mod hk, because hk is trivial. So hk minus 1 is abelian. Right, that's the definition of solvable, is that each of these successive quotients, which makes sense because the next one is normal in the previous one, these are all abelian. So the last guy, if you quotient, well, the second to last guy, if you quotient it by the last one, it doesn't change. So this is abelian. So by Priceman, hk minus 1 is infinite cyclic. We already know that. It's in a non-trivial abelian subgroup. It has to be infinite cyclic. Every element of hk minus 1 leaves invariant the same geodesic of the universal cover when you think of it as a deck transformation. So let G in pi 1 of m be a generator of hk minus 1, because it's infinite cyclic, right? That means it's generated by a single element. And let gamma tilde be the unique geodesic of m tilde that is left invariant by G. Okay. Now let's let A be an arbitrary element of HK minus 2 and B be an arbitrary element of HK minus 1. Then A inverse B inverse AB, well, this is in HK minus 1 because HK minus 1 is normal in HK minus 2, right? So if I take something in HK minus 2 and conjugate something in HK minus 1, this is in HK minus 1, since HK minus 1 is normal in HK minus 2. And then this is in HK minus 1 also, and that's a group, so this is in HK minus 1. So hence, there exists some integer such that A inverse B inverse A B is G to the n, because this group is generated by G. It's infinite cyclic. But that means that if I apply both sides to gamma tilde, this is G to the n applied to gamma tilde, and that's equal to gamma tilde because G of gamma tilde equals gamma tilde. So I'm being a little sloppy now here. This means the image of, okay, right? Strictly speaking, G of the image of gamma tilde equals the image of gamma tilde, but I don't want to keep writing image. Okay, gamma tilde is preserved by G. So if I do it n times, it preserves gamma tilde. But also, since B is in HK minus 1, B of gamma tilde equals gamma tilde also, right? Because everything in HK minus 1 is some power of G, some integer power of G, and that leaves gamma tilde invariant. So this equation says that A inverse B inverse AB of gamma tilde is gamma, sorry, I can take this B away. Gamma tilde is gamma tilde because B of gamma tilde is gamma tilde. But that tells me that B inverse A gamma tilde is A gamma tilde. So B inverse, which is in HK minus 2, leaves invariant HK minus 1, sorry. Invariant A of gamma tilde. But by uniqueness, this was claim number 1 in Priceman. Since K is negative again, we get that A gamma tilde is gamma tilde, right? Because B is in HK minus 1, so it preserves gamma tilde, and we just proves it also preserves the geodesic A composed gamma tilde. But because the curvature is negative, it can only preserve one geodesic. So that means that this geodesic A gamma tilde equals gamma tilde. The images are the same. So A of gamma tilde equals gamma tilde for any A in HK minus 2. So all the elements of HK minus 2 leave gamma tilde invariant. Hence, by claim number 3 of Priceman, the Priceman proof, HK minus 2 is infinite cyclic. This is why I parceled it out that way, right? Because in claim number 3, we didn't need any assumption of abelianness. We just said if we have some non-trivial subgroup of the group of deck transformations, which all leaves invariant the same geodesic, then it has to be infinite cyclic. Okay. So HK minus 2 is infinite cyclic. using the fact that hk minus 1 is infinite cyclic. And if you look at all these steps here, you can keep repeating it. So repeat k times, we get that h, which is h0, is infinite cyclic. Maybe it's k minus 1 times, I can't count properly. Okay, so that gives you the first part of Bayer's, that h is infinite cyclic. We just have to show that there's no cyclic subgroups of finite index. So this last half hour of the course is just group theory. So it remains to show that there does not exist any cyclic subgroup with finite index of pi1 with finite index. And again, this is going to reduce to we used Priceman's theorem a couple of times, or at least we used Priceman's theorem in step 1, and then we used the claims in the proof several times. We haven't used that non-abelian theorem yet, and that's where we're going to use it here. So suppose H is a cyclic subgroup with finite index. We need to get a contradiction. Okay, so the hypothesis is that this is cyclic, so it has generated by a single element. Let G be a generator. So we're not even assuming H is infinite, right? And let G be a generator of H. Let gamma tilde be the unique geodesic in M tilde, G tilde, left invariant by G. Again, we're using the facts that we proved already, right? That this is a generator of H, so it's not, because H is non-trivial. This is not the identity, so there it leaves invariant a unique geodesic because the curvature is negative. And let A be in pi1 of M minus H. And remember, we already said that H had to be a proper subgroup when I stated the theorem, because if it wasn't, we already get a contradiction to the non-abelian theorem. So since H has finite index, there exists some integer n in Z such that A to the n is in H. Okay, that's exactly basically what finite index means. But then, since H is cyclic, there exists some integer m such that A to the n is G to the m, right? Because everything in H is G to some power. So hence, A to the n applied to the image of gamma tilde is the same as G to the m applied to gamma tilde, and that's equal to gamma tilde, since G of gamma tilde is gamma tilde. So A to the n preserves gamma tilde. I claim that means that A preserves gamma tilde. So A to the n leaves invariant gamma tilde. There exists a unique geodesic beta of M tilde such that A of beta is beta, right? Because A is also in the fundamental group and it's not the identity. Therefore, it leaves in, because the curvature is negative, it leaves invariant a unique geodesic. But that means that A to the n of beta equals beta, and by uniqueness, beta equals gamma tilde. So A of gamma tilde equals gamma tilde. So basically what we're saying is, if you know that some power of an element of the fundamental group leaves invariant a particular geodesic, then that thing before you took the power leaves invariant that geodesic. So hence, every element of pi1 of m leaves gamma tilde invariant, right? The assumption was that H was cyclic and G was a generator of H, so there's some gamma tilde that's invariant under G. And then if I took anything in pi1 that wasn't in H, because of the finite index assumption, and because H was cyclic, I was able to show that that thing also leaves gamma tilde invariant. But then by claim 3 of Priceman, the Priceman proof, we get that pi1 is infinite cyclic, right? Because the claim 3 exactly said that if you have some subgroup of pi1 which leaves invariant, which all the elements leave invariant a single geodesic, then that subgroup is infinite cyclic. But now we've taken that subgroup to be the whole of pi1 family. Everything in there leaves invariant gamma tilde. But this implies pi1 is abelian because it's infinite cyclic, and this contradicts the non-abelian theorem. So that's it. So there was some geometry in this proof, but it was mostly group theory. And it tells you that you really know quite a bit about the structure of the fundamental group for a compact manifold of negative curvature. So as I said, this has been pushed quite a bit after the book was written. We know far more now, especially even up to non-positive curvature. You can look in the early 70s. I'm sure some of the references are Indo-Carmel. Some of it had been done, but Yao has done a lot of work about this, and some other people. I wanted to say one comment about chapter 13, which we're obviously not going to talk about, which is the sphere theorem. I encourage you to read it. As I said, it's really hard to read that chapter. Parts of it are a lot of details missing, but essentially it says if mg has sectional curvature k between 1/4 and 1, it's not a constant. If it's between 1/4 and 1, this implies that M is isometric to the round sphere. Isometric. No. M is homeomorphic to the round sphere. If you have a Riemannian manifold which admits a Riemannian metric whose sectional curvature is between 1/4 and 1, then it's homeomorphic to the sphere. So what did I want to say about this? Of course, if we know it has sectional curvature bounded above by something strictly positive, then so does the Ricci curvature. So Myers will automatically imply that this is compact. So M compact by Myers. Right? There's no way you can have just even the lower inequality without being compact. And if this is sufficiently pinched like this, it has to be homeomorphic to the sphere. And that's all they knew, a long time ago. But in fact, recently, and this I'm saying less than 7 years, this has been improved improved to diffeomorph it to the sphere. Okay, and this is called the differentiable sphere theorem. Differentiable sphere theorem, and this is proved using Ricci flow and some other ideas. And so it's proved by Rick Shane and Simon Brendel. And the two of them, I think, have a book called The Differentiable Sphere Theorem, which came out less than 4 years ago. So if that interests you, you should look at that. And there's other stuff in chapter 13 that he builds as a sort of prelude to getting to the sphere theorem. And that's the notion of cut points and cut locus. We talked about conjugate points, and we hopefully got some feel for what conjugate points are. Cut points are another kind of special point along a geodesic. There could be lots of conjugate points along a geodesic segment, but we know now that they're discrete and there's finitely many on any geodesic segment. And bad things happen once you pass a conjugate point, right? And at every conjugate point. But there's a cut point is something that can only exist once if it exists at all. It's the time at which you're no longer minimizing. We know that if you pass the first conjugate point, you're definitely no longer minimizing. That was on assignment 4. Okay, so if there's a cut point for your geodesic, if there's any conjugate points, then the first conjugate point is the cut point. But you might have situations where there's no conjugate points, and yet you still have a cut point. It still fails to be minimizing after some time. So for example, on the cylinder, if you go around the equators of the cylinder, there's actually no conjugate points. You can do that calculation. But certainly if you go around more than once, it fails to be minimizing. So there is a cut point. And you can do various interesting things with the cut points and the cut locus, but we obviously don't have time. So we're basically done. Let me just give you some good references if you want to read more about more advanced Riemannian geometry. So the Bible for all geometers of any type is this 2-volume set by Kobayashi no Mizu called Foundations of Differential Geometry. Foundations of Differential Geometry, volume 1 and 2. And it has all of this and it has way more. I mean, everything that was known when it was written is in there. It's hard to read though, it has some very old-fashioned notation. And so I wouldn't recommend it as a textbook for anyone, but if you're already familiar with some of these ideas and you want to see more, this is a great reference. There's a book by Cheeger and Eben from the 70s. This is old, in the 70s, called Comparison something. Comparison Methods in Riemannian Geometry or Comparison Geometry. Anyway, there's only one book by Cheeger and Eben at all, and this one has the word comparison in the title. A lot of what we did, basically everything we did in the course should be in there somewhere. And then there's a new book, well, newer than these two, by Peter Peterson. It's a GTM, and I think it's just called Riemannian Geometry, which is very well written, but it's a slightly higher level. It goes quicker than Do Carmo. And but this is, I think you're now ready. If you're interested, you're now ready to look at Peterson's book. The Lee's book is also good, but it doesn't go as far as any of these. Right? Okay, so that's it. Are there any questions?